Hi there. Welcome back. So, today we're going to continue on our discussion of classical conditioning and how how some of it works and how it incorporates a little bit more than just contiguity. Remember the little laws of association. There is resemblance, contiguity, and contingency, or as I've referred to it in the past, causation. Right. So last time we went over some fundamentals of how we can adapt our behavior to an understanding of the world around us, right? So habituation, how we can sort of get used to stimuli. We let go of an initial reaction as we experience a stimulus more and more, and also the neural basis for that being, it's kind of energetically efficient, and there's a natural consequence of how neurotransmitter works. We also looked at classical conditioning, right? So how we can pair stimuli to produce new response patterns. If you recall the Pavlovian dogs, you ring a bell, you present them with food, and then they learn an association, right? So recall the laws of association. There's resemblance, contiguity, and contingency or causation. Today we're going to talk about how contiguity is sort of the most straightforward way we can think about classical conditioning, but there seems to be more to the picture, and that contingency is important for understanding classical conditioning. So let's get into it. Classical conditioning, it relies heavily on contiguity, right? The conditioned stimulus has to come, at near, specifically before, and we'll get into why that's interesting, the unconditioned stimulus, right? They have this temporal contiguity. They more or less co-occur in time. That's part of how we're able to form these associations. So remember, the basic pattern is on the left here. We have the early trials where we're just starting the conditioning. We present the conditioned stimulus. We have a little bit of a delay, and then the unconditioned stimulus comes. So we ring the bell, and while the bell is still fresh in still happening, right? The auditory signal is still there. We then present the food, and then salivation. The food has come. So on the top we see the response pattern. In later trials, we do the same pattern, but the dog starts to salivate early. As soon as the bell rings, we see, salivation is happening, right? This just demonstrates, this is the simple effect of how this works, but this also demonstrates the idea that these things are related in time. They're connected together, right? Both stimuli are presented more or less together. So let's stretch that out a bit and look at the edges of this phenomenon. So what happens if we delay that stimulus? Can we push the limits of contiguity? What happens when we shift around when each, the conditioned stimulus and the unconditioned stimulus are displayed? At some point, you'd say it obviously becomes, they stop being contiguous, right? They don't co-occur in time anymore. They're just two separate, unrelated things that have happened. But too early, and things get a little bit messy too. So, we might end up ignoring one of the stimuli because we haven't had time to process them. So this is just a sort of a preview of some of the ways we're going to pull this apart. So let's talk about long delay conditioning. If we extend the presentation delay long enough, we still get the conditioning patterns, right? But and at first it's the same. The conditioned response will occur with the conditioned stimulus as normal, right? So in early conditioning, we have a very long delay here between the bell and the food, right? The conditioned stimulus happens first. We wait quite a while, and then the food appears. Quite a while being, seconds, right? But this is interesting because this is pushing the edges. For a while during this conditioning, the salivation begins as soon as the conditioned stimulus appears. But later, they start to learn that, the stimulus does mean food is coming, but it's not coming for a while. I don't need to salivate yet. I don't need to waste my attention. I can just sort of learn there is this delayed pattern. So we see contiguity can be stretched a bit, but we see that we have a little bit different response pattern associated with a longer delay. What about if we presented the stimuli simultaneously? Well, as I mentioned before, this is kind of a problem. The conditioned response ends up being really weak or non-existent. So the connection just doesn't form. If I present the food and the bell at the exact same time, they don't connect. Just empirically in the data, the association does not get formed properly. So what are these two things kind of pointing at? Well, there is sort of an ideal delay time for conditioning. The exact delay time might be different, but we can't present the conditioned stimulus, right? The one that we want to pair with a new action. So the bell can't come immediately with the food. That just doesn't work. There's no information about the bell and the food being related available. It's just sort of simultaneous chaos. The dog will see the food and just be excited about the food, right? But there's also, you take too long, the stimulus effect starts to drop off as well. So this is interesting. This points to the idea that there is sort of an ideal delay. And we can see this in human studies using, if you try to produce an eye blink response in humans, using a conditioning scenario, usually with light and little puffs of air. It's an annoying study, but it's fine. Totally safe. The older adults they need about a 1 second delay for the conditioning to be maximal, but younger adults only need a 0.4 second delay. Just an interesting little tidbit. It's pointing at the idea that even within the same species, within the same organism, you might have different patterns of this ideal timing. So, okay, let's keep sketching these edges of this pattern. What if we put the unconditioned stimulus first? Well, that's the same kind of scenario as presenting them simultaneously. The dog's not going to learn much about the relationship of a bell and food if they get the food first, right? The important and useful event, the food, has come first in time, and now the new event is not really relevant. It's not really interesting. It doesn't really signal much. Well, why is that? We saw that the simultaneous presentation doesn't really work. Why is this happening? Well, here's an interesting thought on that. If contiguity was the full purpose and the full driving factor of how to form new associations in classical conditioning, then wouldn't we kind of expect simultaneous presentation to be the best? It's the maximum overlap of, these two stimuli, they mean the same thing. Okay, so that would be this kind of curve, right? The delay would be, early on, the two stimuli are presented with the further apart the stimuli are presented from one another in time. The left being the unconditioned stimulus comes first, and then off to the right being the unconditioned stimulus comes after. Maximum would be right when they're directly over top of one another. Present the food, present the bell together at the same time. Contiguity is the key. That's not the case, though. We have this phenomenon of we need the new stimulus, the conditioned stimulus, the bell. It needs to come before the actual, the raw, the unconditioned stimulus, the food. So let's look at temporal conditioning to try to unpack this. It's a little bit different spin. There actually is no conditioned stimulus. It's just you present the unconditioned stimulus at regular intervals. Another way to think of this is actually that time is the stimulus. There's some theories about how we're able to detect time, but point being, If I present the unconditioned stimulus over and over in the exact same pattern, organisms like dogs and humans will learn to start salivating just before it appears. So this conditioned response can come out of no actual conditioned stimulus. It can just start happening because we're able to detect this pattern. This points to something useful. This points to the idea that being able to predict something is the key element of conditioning, which leads us to contingency. So temporal conditioning shows that, it can occur even without a paired stimulus, and it also gives us this important idea that prediction is key. So now we're on to the contingency and causation law, right? So this is interesting. So let's talk about this. First question is, okay, then is contingency the only thing? Is if causation and contingency is part of this equation, do we need the contiguity? Does that actually matter? Can we just get by with things that predict other things being the way we condition? Can something far away in time predict something else? And trace conditioning can help us sketch this out. Under normal conditioning, the stimuli will overlap to some extent, but we can separate them so that the conditioned stimulus will end before the unconditioned stimulus even starts. So that being, ring a bell, wait a minute, maybe a minute's too long, but wait time enough that the bell is no longer connected to like in actual overlapping time to the food. And the reason this is called trace conditioning is that people and all organisms rely on a memory trace of the stimulus to be able to make the pairing. It's similar to normal conditioning where the stimuli overlap, but the effect is a little bit weaker. So, okay, what this is pointing to is that we sort of charted all over the space, right? How far away in time can these things occur? There is a certain stretch of time where, there's a delay in the presentation of the new stimulus, the unconditioned stimulus, right? Delaying that, we can still rely on memory to make these connections, but at a certain point we lose it. We lose the ability to draw a connection. The conditioning won't happen unless either the stimuli are together in time or they're close enough that memory still works. So we're charting this full space, and what we're seeing is that contiguity is necessary for conditioning to happen, but it's not sufficient for the actual conditioning to occur, right? We need this contingency. We need this predictiveness. And that seems to be what conditioning is all about. So a general principle is that contiguity enables detecting contingencies because of the way that our mental systems work, right? We need things either to be actually active at the same time in our neurology, or at least hanging on from a memory to be able to be related. You wait too long, this is why the advice is for when you're training a dog, for example, if your advice is, or the common advice is, if you don't catch the dog doing something wrong, then you don't punish them. There's no point. They won't be able to draw the right conclusion. They'll, they poop in the living room and it's been 6 hours and you come home, and you're mad, right? But the dog doesn't know anything about what you're going. If you now punish them, they will have no understanding of why that is, right? Because we can't talk to them and reason about it, and then we can't reactivate their memory trace, and they're not doing the action right now. So the point being that we need contiguity to detect contingency. We need things to be close in time so we can make stronger conditioning patterns. We can make stronger associations. But it doesn't work in reverse, right? We can't do backwards or simultaneous conditioning. We have to have one stimulus signal the onset of a new stimulus. So, sorry, I said new stimulus. I mean, An unrelated stimulus must signal the onset of an unconditioned, like raw stimulus, like food, right? So the bell has to predict that the food is coming. Otherwise, there's no point in memorizing anything. So prediction. We're seeing how conditioning sort of relies on this. We're seeing the importance of both contiguity and contingency for being able to detect these predictive patterns. And we're also seeing that contingency needs contiguity to get the job done. But why would this be useful? Why would we want to be able to predict things? Why would we be so tuned to automatically take in information from the environment that is predictive of other information? So why is this prediction so good? And what kinds of behaviors can we even condition to figure these things out? One theory about this is the prefiguring hypothesis, and it's sort of explaining conditioning, why it exists as a whole, right? What's the point of this process? And the idea is classical conditioning optimizes interaction with an upcoming biological event. Now, biological event, we've talked about it already, the idea of the unconditioned stimulus, right? Typically something useful or important about our biological existence, right? So unconditioned stimuli are typically these innate reflexes, and those innate reflexes are almost always related to biology, right? A bang, a loud sound means danger, or maybe a roar means danger. Good smells mean food, and in fact, the reason we think certain smells are good is because they mean, hey, salt, fat, those are good. Those are good for survival, that kind of thing. So, okay, if the idea is that classical conditioning is a process to allow us to predict biological events, then let's explore that. So, given any stimulus that predicts food, the organism will adapt to seek out that stimulus as well as food, so that they have an easier time of navigating and surviving in their world. Imagine a cuttlefish. You may not know what those are, but they're little tentacle mouth, little interesting critters. They're related to squids and octopi, and it has to make sense of the seabed, right? It needs to look for food, and it can just blindly do that. But perhaps better is if it had no ability to pick up these associations in the world, it would just have to blunder into food, hopefully. But by being able to detect things like, oh, these little holes in the ground, in the seabed, are predictive of some little critter being down there that I can snatch up and eat, right? The sea is full of jerks. But the idea being that the more you're able to associate things that predict important biology, these regularities in the actual world, the better we can handle survival. So let's look at a study of mouse mating, right? Another important biological event. Oh, a mate is here. We can procreate. Yay, So in this study, you'd pair the presence of a mate with the presence of a mate, right? So, oh, I see a mate. That's great. I will look forward to mating potentially. Now, if you pair that with a stimulus, right? The little blue mouse hears a bell and sees a mate, then of course arousal happens when they hear the bell, right? But the idea here is, this is a simple effect found in a pretty simple study. The idea, though, being that, okay, if I can find stimuli that predict mating opportunities, that might be useful. Maybe I need, in birds, maybe that means I need to, of course, in birds, maybe that means I need to look for nesting behavior. A nest might mean a fellow bird is looking for mating, right? Or with mice, there are certain patterns of behavior that a mate will emit that say, hey, I'm looking for a mate, right? being able to respond to these mating signals is useful for mating. If you're just wandering around hoping to get lucky as a little mouse in the woods, you're probably not going to have much success if you can't read the signals, read the, what are these other animals picking up and putting down, right? So, okay, mating is I hope is pretty clear. This is an important biological event that we're very able to adapt to. We can also look at fish fighting. Like I said, the ocean is full of jerks. So when a rival fish appears, we can expect that a fish who perceives that as a rival will get aggressive. They might start a fight, right? So then, as we do in conditioning, if I present a rival, and condition them to be associated with an auditory stimulus, for example, a bell or something, the conditioned stimulus will now, it increases the number of bites and tail beatings in the fish who was signaled, the one who got the notice that here comes a rival. There is a rival on the way. It allows the fish to be able to predict an upcoming fight and prepare better. Get into the mindset of, I'm going to beat this fish up. It's kind of a mean-spirited study, but that's the way it works, right? That's the way that we uncover some of these things. Also, just a quick note on professional wrestling. I don't think theme music is very helpful. It's just signaling that, hey, prepare. Here comes a jerk. So, although John Cena seems like a nice guy. But let's extend this. What if we, instead of associating the stimulus with a rival fish, what if we associate the stimulus with the lack of a rival fish? So if I only have the light turn on when there is no rival fish coming, that conditioning allows the fish to become more willing to engage in foraging and nesting behaviors, things that they would only want to do when there was no, immediate threat nearby. That's interesting. This is showing that, again, the predictiveness is what is key here. The usefulness of these associations is, can I expect that there will not be a rival coming? And if I can rest assured, if this, the stimulus always means here comes a rival, or rather there is no rival, this is the safe signal, right? Then it allows them to make better choices about what to do with their time in the environment. Interesting. So we've been talking about conditioning more or less around biology, right? This idea that classical conditioning helps us build up predictions about things that will affect us biologically. And so why, though? I mean, it's starting to make sense, I think, that that would be useful, but is there more to that picture? Well, there's the optimal time allocation hypothesis. Then this works alongside the prefiguring hypothesis. They're not in competition, really. The idea being that conditioning will also help to optimize our time resources, right? The idea that, you only have so much time, you only have so much time in the day, right? And every useful activity, at least biologically, takes some kind of time or effort for the organism to commit to, right? Foraging for food, nesting for a place to stay, these things take a certain amount of effort. And being able to predict what's going to happen in the outside world, and understand the signals of my environment, keeps you situationally aware. And lets you develop even better habits, right? So not only is it just, are the stimuli happening regularly, but as we saw before, we can get sensitive to timing patterns, right? So this lets even larger patterns emerge. So all in the idea that I can come up with a daily routine based on understanding what parts of my environment signal important things. So, okay. If that's how it all is working together, which I hope it starts to make sense, then how are we actually picking out which stimuli are related to the biological events, right? Imagine like a world where I have no idea what signal means anything at all. All the events are equally likely because nothing is predictive of anything else initially, right? But you start to piece together which stimuli in the environment are actually signaling the important events, right? So what imagine a crosswalk. If you didn't know anything about what a crosswalk did, you just see weird colored lights moving around in different patterns. You wouldn't be able to make sense of it. But gradually, you might start to pick up in this crosswalk world. You might start to pick up, oh, well, the traffic, these big metal beasts stop moving when the signals are a certain way, right? So the question is, though, how do you figure that out among all the other stimuli available in the world? So let's think about the mouse scenario. Um, the mouse in the cage is surrounded by stimuli. Everything outside the cage is just so much available, right? The mouse learns to operate a lever because food is associated with it, right? But how does the mouse know it's not the time of day, or the sounds coming from outside, or the clock, or the lights and the other ambient sounds, the fact that there's a person nearby, the door is open or closed, what's happening outside the door. There's so much stimuli. There's so many stimuli always bouncing around the environment. So the question is, how do we effectively draw the correct conclusions? How do we make a connection between one stimulus among many, many, many stimuli to this response that we want to make sense of? And this is known as it has a few different names, but the problem of projectable predicates. Well, I'll break that down real quick. Predicate just means it's the necessary condition for something to occur. A cloud is a predicate of rain. It has to like exist before rain happens, right? But projectable means we have to select it. So there are many possible predicates of rain in a world where we don't understand anything about rain yet. And we have to figure out which ones are related. So this is also known as the problem of induction, or the problem of credit-blame assignment. So how can we address this? What are the features of stimuli that might make them more apt to be associated with some important biological event? So, okay, here's the basic setup of the studies, or the effects we're going to look at based on studies, but we're not going to really cover them in depth. Present food alongside two equally identically unrelated stimuli, right? A sound and a signal, right? A visual, a light bulb or something, right? So, and they both always equally predict the food, right? Which one is going to get associated with the food? Like if I do this and then test them separately, will they both signal the food? Or will only one? And if only one, why? So which stimulus from the environment is actually going to form the association? There's a few different phenomena that have come out of this, some observations about how this stuff works. First is overshadowing. So all things being equal, again, I present a very bright light and a weak sound, right? Same presentation time, same everything, right? They could be considered the same stimulus, but they have different sources, right? The more salient one, and that's a term that comes up quite often in cognition, the stronger or more noticeable stimulus, right? The one that produces a stronger internal response from our neurons will overshadow the weaker stimulus. So if I present a very bright light and a weak noise with the food, only the bright light receives an association. The weak noise is discarded. It's considered less relevant. What else might interfere with this? So another phenomenon is called blocking. That this is the idea that if I already had one of the two stimuli I'm now training was previously associated with this stimulus, it will win. It'll win out. So again, we present food and sound, right? Classic Pavlovian dog training. Sound elicits salivation, right? Pair food and sound plus light in a second round of training. Light doesn't do anything. It's not adding new information. It's not giving anything new to the prediction structure because it's being presented at the same time as something that we already know signals the food, right? This is actually quite useful. You can imagine how this would help. No. The important thing is the street light, not what the dog across the street is doing. Just because people always are co-located with the crosswalk doesn't mean that they are the actual signal. It's the previous one that I already learned. Now, that implies a lot of higher level reasoning, but the idea is that this is sort of the way that things shake out in nature, right? If I learn one association, I don't necessarily want to be constantly tweaking it. I need to have strong evidence that it's not a good association, right? Whereas if I just was able to adapt a little bit too often, I might lose the usefulness of this prediction. So, okay, but those are pretty clear scenarios, right, where one stimulus will win out over the other. The really strong stimulus and maybe a previous learning with the stimulus. But what if everything was legitimately equally, exactly the same about these two stimuli? Neither of them had been previously trained. They're controlled carefully to be the same salience, something. And that gets us into the scenario of equipotentiality. And that is essentially, who cares? It actually doesn't matter if one of these two, if given two equally predictive stimuli that seem to always occur together, then it has the same utility. You don't need to have a lot of information about this. You can just pick one at random and get on with your day. Just move on with your life, right? So this is kind of a key piece of the puzzle because it's the idea that our system, as much as it seems like there is a really important guiding principle, it's really just trying to make connections to the outside world, and given two equal things, doesn't matter which one I pair. That doesn't mean that there aren't other factors that will influence this new association, but it does mean that it's not necessarily meaningful, right? If lightning and thunder sounds always signal rain, I don't need to pick which one signals rain, right? So, okay, that's a basic principle that when you boil right down to it, it doesn't matter which one you pick, as long as all things are equal. But we can keep drilling down a little bit, and we actually see there are some things that seem like they should be equal, but are not. So let's talk about primed responses. So some things are just more apt to be associated, even if they seem like all things should be equal. So one good example of this is in taste aversion learning. We're going to talk about this later too, but we'll start with it here. So here's a simple taste aversion learning study. Pair both light and flavor stimuli with either shocking at a short delay or radiation at a long delay. So similar structure, right? I present the mouse with water, and the water has a flavor in it, and I shine a light stimulus. And then I will either subject the rat to a dose of radiation that makes them feel sick, or I will subject the rat or mouse to a dose of an electrical shock, right, on a short delay. So then we break it apart and we present each stimulus individually, right, to each rat, each mouse, each organism. The rodent will, so if I present light directly, to the and not the flavor to the rodent, then the ones who were shocked will show more avoidance. The ones who were radiated don't care about the light, strangely. On the opposite side, if I just present flavor, the rats who were irradiated will show avoidance to the flavor, but they won't necessarily care about the light. The light doesn't signal radiation to them. So we can see in the results of the percent rats who would actually drink from the water, when I present the flavor, the short delayed, the ones who were shocked versus the long delay radiation, they drink. They're fine. They don't care about the flavor. They learned to associate light with shock. Opposite pattern for when I present the light. So the ones who were shocked avoid the water because they don't like the shock, right? But the ones who were irradiated, if I present a light to them, they don't mind because they don't associate the light with the illness that they felt. You're seeing, I hope, that this is showing that flavor is more apt to be associated with illness and light is more apt to be associated with a direct physical shock. Why? That's interesting. Why would that be? So, again, here we're showing, the radiation doesn't pair very well with light, with like a light stimulus. It's both slower and the strength of the acquisition is worse. But opposite pattern with shock. If I'm giving a shock as feedback, flavor is poorly received. It doesn't really associate very well. It would take a lot more trials to associate a flavor with a shock than it would to present a light with a shock. Why? Well, preparedness is the concept here. Organisms have a predisposition towards certain associations, and that's because that's how nature works for them, right? So why might a rat associate illness with flavor? I think phrasing like this makes it make pretty clear sense, right? A rat eats something, they get sick, right? But why might a rat be predisposed to associate shock with a visual stimulus? Same idea. They're not going to see much in the world that makes them sick, right? They have to taste it for it to make them sick. That's the idea, that there are more prepared, automated associations, things that are ready to be learned, and there are associations that are much harder to learn. So, let's think about this a little differently. Wilcoxon, Dragoin, and Krall, 1971. They did a study of quails and rats. And they have very different patterns. Let's just focus on the illness part for explaining. Rats are more apt to, they have a more prepared association between illness and flavor, while quails have a more prepared association between illness and vision, visual stimuli. What's the difference? Why? Well, rats live, they have completely different food strategies, right? Rats live, mostly underground. They're nocturnal. They don't rely a whole lot on vision for determining what's going on with their food. They do everything based on scent and therefore a bit more close to flavor. Whereas a quail, they make sense of the world in terms of, they eat based on sight, right? They have to pick out which berries or bugs they want to eat. And if they eat a very bright yellow and red bug, they might be getting into a scenario where they are poisoned, right? Less about the flavor of the bug. It seems like all bugs are kind of more or less the same, but that the kinds of stimuli that they have to be sensitive to are visual. So this is the idea of preparedness. And preparedness seems to go hand in hand with your species, right? But there's more. I mean, the specific to your species, but also the environment you are in and other factors. So, what is it that's determining preparedness? And that's the kinds of associations that you can pick up. Is it just your genetics? Is it just your environment? Is it more complicated than that? Are we looking for too simple of an answer? And spoiler, yeah, of course we are. So let's look at some weird examples. Preparedness for chick pecking. Baby chicks, within 2 days, they start pecking at mealworms. It's one of their favorite foods, and they start eating it. But here's a weird thing. If you cover the chick's feet, they stop pecking. What? Why? The answer is complicated, and it's highlighting the idea that it's not always clear. We have a lot of very nice examples of very straightforward connections of how we process the environment, right? How we deal with stimuli. But this one doesn't seem to make any sense on the surface. Why would covering their feet change how they behave in pecking? It could have to do with the way they sense the world. Maybe they need their feet to sense the mealworms in a certain way. Maybe they need their feet to sort of sense of their feet for balance or something. There are lots of ways that interfering with any one part of this bird's system will make it sort of primed differently. Also, just covering their feet. There's no harm done here. How about with a different phenomenon? Fear of snakes. Fear of snakes is a good fear to have, right? It's pretty important to stay away from snakes. They don't have a lot going on except they like to bite. And you don't want to be near them when they do. Okay, so here's an interesting phenomenon. If you feed a monkey only fruit growing up, they don't have any fear response to snakes. But if you feed monkeys fruit and insects, they develop a fear response to snakes. An intrinsic one. They're more apt to have the fear response. Again, what the heck? What does a chick's feet have to do with pecking? And why do insects influence fear responses? And the answer is in complexity. Now, this is something that I will pass the buck to continuously, but it's almost always a key factor. Not everything is clear and straightforward. Even these sort of simple effects we've been examining, there's a lot going on inside of the cognitive system and the bodies and the environment that are all interacting all the time, subtly. So sometimes the connections between these, what seem to be innate predispositions, and the developmental events, and then the way that things in the environment are actually associated, way stimuli are associated naturally, they all combine to make this really complex and non-obvious interaction go on. So preparedness is a very useful concept for understanding what might you be most likely to automatically learn, mostly as a species, but sometimes on an individual basis. And but the fact that there is a more complex story to some of these things. It's not easy to pull apart all of it. So let's recap. We've looked at conditioning, and it's a way to create associations, right? I compare new stimuli in the world with to create new associative interactions. But it seems like its role is mostly to help us detect these contingencies and understand cause and effect in the world to some extent. But it does require a certain amount of contiguity. I can only notice what things are sort of co-located in time or co-occur. And we've also seen that some stimuli are more or less likely to be associated as signaling certain events. Preparedness, salience, previous learning, informativeness, all that kind of good stuff is useful for understanding which stimuli are likely to get paired in the natural world in our understanding of it. To cap this off, let's talk about an interesting exception to this rule. Taste aversion learning, like we talked about before, In those rats, it is really fast, and in terms of the number of trials it takes to learn taste aversion. This is strange, right? Normally, this takes a lot of effort, but taste aversion can be almost one shot, known as one shot learning, where a single exposure can be enough to form a pretty strong new association. And it's very resistant to extinction. These things don't just go away. You eat something and it makes you sick once, it's pretty useful to be able to quickly adapt to that behavior. So, and it's present in very many species, though it's maybe response to different stimuli, and it it's kind of funny though. It presents a problem to our general approach to conditioning because it kind of violates the law of contiguity, right? It occurs on a pretty long delay. I eat something, and then I instantly learn after one delayed response. Oops, this is bad. Normally that would be a pretty weak effect, right? It also screws with equipotentiality. So one of these stimuli is quite preferred. In fact, this taste to illness thing is pretty common. Now, we talked about how birds seem to associate vision with illness more readily, and that makes sense because of the way that they live, right? But they also do have the ability to learn these taste aversions because that's still going to be useful, right? You learn that the chemical compounds present in something might help you determine whether or not it's going to make you sick. So one theory is that taste aversion learning operates on a completely separate learning mechanism than all these classical conditioning ideas. And, it kind of makes sense, right? It evolves from a need to avoid noxious stimuli in the environment. And that's like every organism that was ever an organism needs that, because chemical detection is one of the first things we learned, right? As an evolving entity, as one of the first abilities we needed to master, to seek food, but also avoid bad things. So a little bit about this is that rats and many other omnivores will sample a novel food source, and then they'll wait several hours before returning for more. They delay themselves and say, hey, I need to see if this thing's going to make me sick or not. Their behavior adapts to this unique learning mechanism, right? They're I wouldn't necessarily say they are aware of it, but they employ it pretty strongly. It's an important step for them to test food first because they want to allow for this really important learning to take place. Whereas most other conditioning is a little bit less, it guides behavior a little less until it's actually formed. So this is nice. This is a good theory because, in terms of if we like classical conditioning, this is good because it allows taste aversion learning to be sort of a separate idea that works in concert with classical conditioning, but is sort of distinct. So to illuminate that a little more, taste aversion learning is this unique pattern of learning, and it varies across species, but it only really varies in quantity, not quality. So, for example, we saw that rats learn this taste illness association really quickly, but birds don't learn it as quickly, right? But they do eventually learn it. So, one of the key ideas here is that, and this is useful in all of science. So, this is not a difference of kind, right? The rats are learning rapidly this association, but birds can still learn it. So it's this fundamental system that is in most organisms. Birds have adapted a different strategy over top of this, but it's still present. And so the point being that this is not a difference of the dynamics. It's the shape is the same. It's just sort of about the speed. So rats learn much more quickly. It takes them 3 trials, whereas birds, it might take 3,000 trials. But they still are learning in the same way. So taste aversion is separate, but it operates alongside classical conditioning. And, the birds will learn to avoid things. They'll learn to avoid foods that make them kind of sick. It might take them longer, but they still do. And it's still just as resistant to extinction processes and things like that. So, yeah, we have this kind of unique tool in our kit, in our biological kit, that says, hey, you should probably learn some things about tasting differently than we learn things about like weird random patterns in the environment. This one's really key to our biology, and this is why this is kind of how favorite tastes associate in our lives too. That's why we might immediately start to learn the flavors that we do and don't like, right? Based on the stimulus. So yeah, that's more on classical conditioning. We see there's some variation in the way that it works and the way that different learning styles maybe interact here in terms of the taste aversion learning and other more general processes. But in general, classical conditioning is this useful way of understanding how we can associate ideas in a very fundamental way. Calling back to, remember, part of what we're doing is trying to figure out where does knowledge come from. And this is a good explanation. It's showing us how we can form new knowledge, new associations, new ideas about the world around us from direct experience. And another important thing here is that we've talked about a lot of different constructs, a lot of different ideas about which things are important for understanding, how we will form these new associations. Is it just continuity? Is it just contingency? No, for sure they interact. We saw that like the informativeness, the context, maybe the evolutionary purpose for the preparedness, they're all important. They're all useful, and they will come to bear in different ways. They all influence how we learn these associations. So that's it. Thank you for listening, and take care.